Okay. Can't you think of it as being, you have a mode of oscillation this way, and you have a mode of rotation. And when you do it one way, the energy difference between the modes is like so big you don't like excite the oscillation. But when you do it the other way, the energy of the rotation is enough, is like, so that it's on the same level as the energy of the oscillation. That energy of oscillation has to go somewhere, so it goes into the energy of the rotation in the other direction.
But then it wouldn't that just happen without contact with the table?
Thus you're assuming that there is no dissipation.
Yeah, but like, I think
because if you do it in outer space, you know, and
no, well, you need the friction to give you this, to put you into the oscillating mode, because otherwise you won't get it. Like you did on a free surface, you didn't get the oscillation.
Because certainly when I rotate it like that, it rotates, but it stops faster when it does that, right? So actually, yeah, the energy is being transferred to oscillation mode faster when it's rotating one way
Than the other, yeah.
than the other. But so yeah, that might be one factor, but maybe not everything. And also with the spoons, you know, it reverses in both directions, so that's slightly different. I guess.
But also it seems that it vibrates.
Yeah, it's wobbling the other way. Yeah.
So it actually makes it go quicker than it makes it go for longer than if it were exactly symmetrical, I guess.
I think this mode is less energetic than that one. So it's more.
So maybe the geometry of the object gives you the
Well, yeah, but it seems that it is just
mode and
like
energies.
going like that. So if it was entirely symmetrical, it wouldn't have moved for such a long time in the counterclockwise direction than it does. Because when it should have already stopped, it
Yeah,
still
it keeps
has
going.
got this vibrational energy, so it keeps going. Even though it doesn't reverse the direction,
Yeah.
but vibrations help it to continue moving. What else can you make Rattleback from?
Well, I don't think that's more. I mean, there's a spoon, there's that what you see. You can make it from an egg. You take an egg and then you have to put something there. So I've seen an article in Polish version of Scientific American.
Yeah.
About that. So the guy took an egg or some other egg-like shape, and then he put just a stick like that. And if it's at an appropriate angle, then it actually reverses quite nicely.
Do you have with you this original version of the paper that you have shown with Lyapunov equations?
Yeah.
Lyapunov functions? Well, it's because Lyapunov functions come into play when you are considering chaotic system.
Oh, original.
Oh yeah, that's.
So I was wondering if this is not actually a model of the chaotic system.
References.
Yeah, but do you have this paper on your computer?
Okay. That's not.
I wanted to see the paper actually.
Yeah. I'm just showing that for completeness. Yeah, it's here. That might be.
Because it looks very interesting.
I think the Lyapunov one is old. Yes, is this?
Oh yeah, so it's this page.
So it's older. And
Okay, so just the first page, if you could zoom
Yeah.
it in. What are the assumptions?
and there's. Yeah, that's not entirely understood. I said that because there's another paper. It's a newer one, which says that this paper uses some strange maths, which is not congruent with reality. Yeah, it's.
But they use nice maps. So
Yeah.
what next? If you slide forward, okay, mathematical model. That's the most important. Okay. Right. So they do exactly what you have done, but just writing it out in long form. Mathematical model is Lyapunov stable, so they actually consider it to be a chaotic system, driven chaotic system. That's cool. What's T? Is it a torque matrix or something like that?
diagonalize the matrix P.
Okay. What then? Oh right, then they use the Lagrange, Euler Lagrange. And they find equation of motion.
It's only given us an equation,
Yeah. It is actually an equation of motion. Because they've just applied the Euler Lagrange. And here you go. That's for one component, and then for another component. And then for the last component. And they actually predict what is the orbit, the second orbit
right?
of the movement, the eta square root of 2 cosh. I don't know what is actually eta. But it looks just like in Newtonian orbits, when you first get the time derivative for components, and then you get rid of time derivative, and you just look at the shape of the orbit itself.
Okay, I'm going to show you something else.
It's really nice.
The new one.